First up, we have Wendy Parker from Durham. It says LSE on here, that's not right.
That's because it used to be Lenny's slot, and
Yeah.
they just changed the name.
Wendy Parker from Durham University. The title of her talk is Talking About a Revolution.
Yeah, which is not the title that you would see in the flyer, because as I said, I'm sort of taking it over a spot for Lenny because he's filling in for Jupiter Curry. So this is really a talk that's mostly me just describing a situation and offering a few reflections, and my hope is that you're mostly going to talk a lot about it, especially the climate science people. But anyway, something that I think is really interesting, and we'll see how it goes. I'm sort of thinking about this together with Joel Katzev these days, but mostly what I'm going to talk about is, as I said, a little bit more descriptive, and I think we're still trying to figure out what we want to say, constructive and beyond what the state of the affair is. So, all right. So, as many of you know, right, there are a range of climate model types. We have everything from energy balance models to global climate models to their closely related cousins, the Earth system models that sort of add in, say, biogeochemical processes. But people often describe this as a kind of hierarchy of models from the simple to the complex. I'm going to come back to talking a little bit about hierarchy that's in a slightly different way than that kind of talk. Yes? I didn't leave you off. There you go. You were getting serious. I wasn't baiting you, I promise.
Oh,
and I was going to say, and we also have, of course, regional climate models that we'll let Linda talk about, which are sort of focusing in on a particular region and often are at a much higher resolution. So this is quite kind of a general, very coarse picture of a family of kinds of models that are in use. All of them would be said to be important, and I think that I certainly agree with that. But it's also the case that GCMs and ESMs, the sort of complex end of the spectrum of climate models, seems to have been more or less occupying the center stage in the last decade or more, let's say. So I think there's this perception that these models are getting a lot of attention, though at the same time agreement that all of the types are important to doing science. So as I say, I think that these kinds of models have come to occupy center stage. In part, that's because there's this belief that having more detailed, we might say more realistic models, that this is just better for a lot of the purposes that we want to use the models for, including things like detection and attribution, projecting future climate change. Not that this is a necessary condition, but that in general it's better to have more of the processes that you think are relevant represented than to have them represented in a finer detail. So there's some rationale for having a lot of attention given to these models. At the same time, a lot of people have commented on what they see as perceived limitations of the current state of affairs, let's say, in climate modeling, which includes the fact that there is this sort of GCM-centric kind of attitude. I'm just going to talk about 3 perceived limitations because those are going to be limitations that figure very importantly in the changes that I'm going to talk about, the changes that are called for in a minute. So here are just a few of those limitations. So one of the complaints is, or one of the concerns, this is related to Linda's talk actually, is that even our complex models still have spatial resolution that's too coarse for regional climate change predictions, and so we end up using RCMs, but then you worry, the regional models, but then you worry a little bit about using GCM results as boundary conditions for doing the kind of downscaling. One of the reasons you worry a little bit is because you think that there's feedbacks going on that are relevant there, not just the boundaries controlling what happens inside. So there's worries about not having, so let's say, adequate resolution for the kinds of things we'd really like to be able to simulate well, the scales on which we think we really need information for things like adaptation planning. Okay, so that's a concern, a limitation is perceived. There's also a perceived limitation that has to do with understanding, which is that it's really hard to understand these really complex models that are getting a lot of attention. Not just because they're highly complex, but this is something I'll come back to in a minute, but also because they differ from the simpler climate models that we have in numerous ways. So the relationships among the models that we have are not systematic and well known. That there's a lot of differences, which makes it hard to know what do you blame the difference in performance on. Is it because there's not, like, they differ with regard to one thing that you could then put your finger on. And then another limitation, again, that is perceived by some is that it has to do with this GCM focus, that this is narrowing our attention in a way that's unhelpful. So that GCMs are so dominant that not enough attention is being given to alternative approaches that we might take, and I'll say in a minute what some of those might be. And moreover, GCMs are so resource intensive that even within our focus on GCMs, we have sort of limited set of models and runs that we can actually pursue because each one costs so much computationally, personnel-wise, all that. Okay, so I'm not saying that these are special limitations that I picked out. These are limitations that I'm reporting because they are limitations that drive calls for change in the way climate modeling is done. And that's really what this talk is about. One thing that I've noticed in, say, the last decade is that we've started to see multiple people, multiple kinds of calls for discipline-level changes in the way climate modeling is practiced. And so one of those, I'm going to talk about a few of those proposals. One is having something like a Manhattan Project for climate prediction. One is having a little bit more focus on what are called hierarchies of lasting value, and I'll explain what those are in a moment. It's already touched upon earlier today, in fact, in Gavin's talk. And then a third proposal, which is really hard to name and even to describe, but I'm going to call it increased diversity. So these are actually mapping pretty closely to those three limitations that I pointed out on the last slide. In other words, those limitations are going to be what drives these kinds of calls for change. So what we're going to see is that these proposals differ to some extent anyway in both what motivates them, why they think changes are needed, and in what kinds of changes they're calling for. And so all I'm going to do in the time that's left is just tell you a little bit about each of them, identify some challenges and questions that remain for each of the proposals, and then I say offer some reflections, but I'm pretty weak on the reflections at this point, so I'm hoping we'll have a good discussion. So the first one, a Manhattan Project for Climate Prediction. Here's maybe a sort of great way of just signaling the kind of thing that is had in mind here. So this is where the title of the talk comes from. This is a paper by Schuppel et al. In the Bulletin of the American Meteorological Society. Revolution in climate prediction is both necessary and possible. It's a pretty... and then they lay out, why they think that's the case. And it's necessary because we need regional scale predictions, so we need models that can resolve things on the regional scale, because we need information at that scale for adaptation. That's sort of the necessary part of it. It's possible because if we pool our resources and do things right, we could have models that have a high enough resolution. That's sort of the argument. We need to have that Manhattan Project. So the goal really of this proposal is that we want improved climate prediction. So it's really prediction that's motivating this. That's the goal. Yeah, the motivation, the sort of limitation that's motivating it is the one I pointed out on the first point on that slide of limitations, the inability of our current models to simulate things on regional scales unless we move to regional models that are forced with GCM boundary conditions. And then, as I hinted, right, the proposal is to pool our resources and have a few multinational climate research facilities with dedicated, very high-end computing capabilities. So right now we have, say, a few dozen models around the world that are GCMs, ESMs, and these are mostly housed at national modeling centers. The proposal here is we need to have sort of multinational centers where we pool our resources, and we have really fast computers, and then we can have the kinds of models we need to have the information. Here's a quote from one of these papers calling for this. Because current computational infrastructures are funded through national resources, no single modeling center in the world has been able to acquire this required supercomputing resources and the critical mass of scientists to build and run climate models with cloud system resolving atmosphere, eddy resolving oceans, landscape resolving land surfaces, to investigate what's really needed scientifically to provide confident global and regional predictions over the next century. So it's like a diagnosis is, we're sort of spreading our resources too thin. We've got all these national modeling centers, and they have their models, but to get what we really need, we need to kind of pool our resources, both computationally and personnel-wise. And I should say, they're pretty clear that when they call for this, they're not saying that we should take away funding from the national centers. They want this sort of like as an additional thing. And then the national centers are supposed to take the great information provided by these centers and sort of tailor it to address the questions that they need to answer for their countries. So the goal is to have really high resolution climate models. So I don't know what the right number is, but something like, say, 5-kilometer, I don't know if that sounds right, Linda, but something like 5-kilometer resolution instead of, say, 100-kilometer resolution, which means a lot more computing required. And another thing to mention about this approach is that what comes along with it is something that is usually called a seamless prediction approach, where we want to have our models set up in such a way that we can kind of use them in a modular fashion. So we could have sort of one unified framework for modeling where if we want to do weather forecasting, we have certain modules active and other ones turned off. If we want to do climate modeling, we turn on some other parts of the model. And the advantage of this, in addition to just having a unified system, is supposed to be that if you can run the models in weather and seasonal modes, this is going to give you additional opportunities for testing your model, seeing how well it can do at simulating those things. And if you see that it's doing really poorly in certain kinds of fast processes, that might actually help you make some improvement to the model that in the end makes a helpful difference to the climate simulation. So it's also supposed to provide these opportunities for improving your model. Just to say something briefly about the seamless approach, so we would say, take a model, look and see how can it do a seasonal prediction, and we could say, do a diagnosis. So this is just a report. This is not using, we don't have these high resolution models yet that are being proposed, right? They're proposing the Manhattan Project. But this is just an interesting figure for thinking about how you could use something like, say, a seasonal forecasting system to, or say if you had a unified approach and you were running your model in seasonal mode, you would sort of look for clues that where things were really going wrong. You would focus your efforts there and see if you could, improve your model in some way on those processes, which hopefully would also benefit the climate runs. But the reason I wanted to show this one is kind of related to the discussions we were having about predictive probabilistic forecasts and the usefulness of information or not. If we don't have the PDF right, do we still have useful information? This kind of discussion. So in this paper, these are so they looked at seasonal forecasts. So they just wanted to predict are we going to be, below normal, about normal, or above normal? So sort of 3 categories, and then the prediction is telling you the probability of being in each of those categories. They did a kind of analysis, and they color-coded it based on the performance, but it ranges from perfect to dangerous. And dangerous means, and in between you have still useful, marginally useful, not useful, and dangerous. And so 2 things to note. First, you actually have every color is up here. Right? So everything from perfect to dangerous.
How can perfect be a category?
Yeah, good. So I'll just show you. I'll put this up to show you. So this is sort of evaluating a probabilistic forecasting system. And what all they're saying is that if you look at the frequency with which the event occurs and compare that to the frequency with which it's forecasted, the probability that it was forecasted to occur, you find that it's consistent with your getting it exactly right. So if every time if you forecast a 30% chance of something happening and it happens 3 out of 10 times, great, right? So if you could get that for all of your categories, you'd be in good shape. There's some uncertainties there's some complications with the calculation, so it's more like are you consistent with it being perfectly calibrated? And then the dangerous case is when, in fact, you're sort of anti-correlated, like.
You notice you live in a dangerous zone.
So, I just wanted to put this up for 2 reasons. One was really just to probe our minds about the ideas that we could do seasonal forecasting kinds of runs where we actually can get feedback on how the model's doing. If we see that we have these dangerous zones, if we have really poor performing zones, we could probe, what's going wrong there, and maybe we could get some insight into how to make some changes to the model that would in turn actually have some benefit in the climate context as well. So that's supposed to be one of the advantages of the sequence. So that was one reason I wanted to talk about it, but the other was just to think about, the idea of having probabilistic forecasts that were still useful for some decisions, even if they were far from perfect. Of course, the funny thing about dangerous is if you flip the sign, then you're back to, you actually got information.
Dangerous. Can I just ask a technical question?
Sure.
And I'll be very interested to look at this article. What was their criteria for making these distinctions in the categories from
Yeah, so
perfect to a university?
it has to do with, as I say, it has to do in a perfect case with whether you're both well calibrated and skillful. And then basically you start getting less calibrated, but if you still have a Brier skill score that's positive, then you get some credit and eventually get to the point where you're not only not skillful, I mean, you're sort of anti-skillful. Okay. So some challenges and questions for this approach. I mean, there are some institutional, so I mean, suppose we wanted to do this 5 minutes. Okay, that means I have to really move. Suppose we really wanted to do this. I mean, there'd be institutional challenges like how do you actually fund and coordinate all of these multinational facilities? There are also scientific questions like, you know, actually building these models is not going to be trivial to build these really high resolution models. Are we going to actually end up losing some of the GCMs at the national centers if we do this? And if we do, you know, is that going to be a problem for estimating uncertainty or probing uncertainty? Tim Palmer, who's one of the people who advocates this approach, says it's okay, we can handle it with stochastic parameterization, and I don't have time to go into that now, but we can talk about that in the discussion period. But there's a question about whether this is going to cost us really in terms of having enough diversity to probe our uncertainty. And then this is the one that I think is the most important though, this last one. Even if we have reliable predictions when we do this, we're not going to know that they're reliable for many decades. By which time we're already going to have needed to make the decisions that they're meant to inform. So, I mean, it might be good to have a system like this, but we won't know that we have a system like this until we've already had to make the decisions. So, there's a question about how much this really somehow solves the problem of urgently needing information. Okay, second one, since I have almost no time left. Hierarchies of lasting value, whose main proponent I take to be Isaac Held. The goal here is really understanding. Having better understanding of the system and of our models. The motivation comes, in large part, is related to this article that Gavin mentioned from 2005, the gap between simulation and understanding, that we seem to be getting better and better at simulating the climate system, but we're not keeping sort of equal pace in actually understanding why things go the way they go. It's not that we're not learning things, but that there's a kind of mismatch in the pace that's going on here. The proposal is to develop hierarchies of models, and they're not just like the hierarchies where we have a range from simple to complex, but the hierarchies are very carefully constructed so that the models at one level are systematically and in a known way related to the models at the previous level, so that you have a better chance of diagnosing the differences in their performance. And moreover, you're supposed to study these in great detail. Here's a quote from a more recent discussion of this of Held in 2014. He says, "This approach is similar in spirit to that used in biology, where a hierarchy of model organisms, from bacteria to fruit fly to zebrafish to mouse to chimpanzee, is used to build an understanding of human biology." So he sort of has this analogy, and what he's really calling for then is, at some point he talks about identifying the E. coli of climate models, a sort of model organism equivalent to climate models, a very simplified model that, as Gavin was suggesting in his talk, that would hopefully stand the test of time, and understanding how that model works would continue to be useful, even as we change lots of other things about other models that we have. And he talks about intermediate complexity models that climate scientists take, quote, just as seriously as do the biologists who map out every single connection in the nervous system of the snail. So the idea is to really understand how some of these models work in their details, rather than just constantly moving on to adding the next bell and whistle to the models that we've got. Here's a quote, "Even the simplest levels of the hierarchies that I have in mind are turbulent and chaotic models that one cannot hope to understand in all detail. My concern here is with models that attack some of the core sources of complexity in the climate system, allowing us to address questions of climate maintenance and sensitivity." It's really a basic science kind of approach to getting traction and understanding features of the climate system. And he says, this is the way I think we have to do things if we're going to make progress on understanding. He's pretty strong. He says he thinks there are no alternatives to making progress in this way. So what about challenges and questions on this approach? And I should be clear, Held is not saying let's not do GCM runs. He's just saying we need to give more attention to the understanding side. We've been neglecting that a little bit. I think there's a cultural institutional challenge here, which is just that this kind of work, systematic analysis of very simple models, my perception is that kind of work is not given the same panache and credibility and status as adding some additional thing to a state-of-the-art model. there's a kind of cultural barrier that has to be overcome. On the scientific side, there are challenges like trying to figure out what the appropriate hierarchies are. And this one I think is the interesting one that relates to sort of reductive approaches in explanation and understanding. There's really a question about how far an approach like this can take us, right? It's an empirical question. How much we learn about simple models can actually tell us about more complex models. So I agree, I don't see a better strategy to tackling it, but it's not like we can just count on this to get us what we want. Okay, last one, and this one's the shortest, so that's good. I know I'm out of time, I'll wrap up. This one is the hardest one to sort of summarize, and I actually think there are different people who have sort of different variants of this kind of proposal. I have Judith Curry up there as a representative in this case, but probably there could be other ways of doing it. The goal here is both Held's goal of understanding and improving decision support. The motivation, as I understand it, in Judith's case anyway, is that with GCM dominance, we're just not paying attention to other ways that we might try to get at the climate system. Here's a quote from one of her recent posts. The numerous problems with GCMs and concerns that these problems will not be addressed in the near future suggest that alternative model frameworks should be explored. In my opinion, climate modeling is currently in a big and expensive rut. So what are some of these alternative approaches and frameworks? Well, there's sort of like a list of types of things we might do, anything from different ways of thinking about how to model the atmosphere. She talks about multi-component, multi-phase atmospheres. I don't understand that one very well. She talks about maybe I just don't understand myself. Stochastic modeling, which is really what Tim Palmer's pushing for. He talks about doing dominant mode analysis to sort of understand sort of drivers of different kinds of models, network-based models. I mean, this is more a plea for thinking outside the box than any specific thing that she thinks needs to be pursued. But the point of this is just supposed to be that, because we're focused in a particular way with a kind of narrow perspective, we're not paying enough attention to quite different ways that we might take to trying to get more traction in understanding the system. Challenges and questions for this one. Well, again, there's this cultural challenge that some of these kinds of approaches are pushing against some of our default assumptions, and they're not popular. I'm not sure that people are going to feel a sort of career incentive to pursue some of these approaches, just thinking practically. And from a scientific point of view, it's not at all clear to what extent these alternative approaches are supposed to be supplemental to GCMs, and to what extent they're supposed to replace them. I think it's, how much can we reasonably hope to get from these alternative approaches? I think that's a real open question for you. So it's like good to tell us to think outside the box, but I feel like that with this one especially, there's a real question about what we could hope to get. So this is just to wrap up then. We have this picture where we seem to have agreement among at least some parties to this discussion that something like disciplinary changes are needed in how we're doing climate modeling, but we have competing visions of what the highest priority changes are, and in those competing visions you find some tensions as well as synergy. So for instance, the Manhattan Project is clearly in tension with, that should be moved away from GCM's 3, that was supposed to be not 2, with the second option. On the other hand, you have Held very clearly saying, look, understanding is good in itself, but also it's a way of supporting efforts for prediction. So it's not like these things are competing practices. Will any of these things actually happen? I don't know. But if you think about who's going to decide whether they do, it's going to be both, individual scientists who are deciding what research projects they want to do, and also institutions. What are our research funding agencies calling for? What are our national plans calling for? And just, this is my last slide here. If you look at the 2012 approach from the report from the NRC on advancing climate modeling, you look at what they call out as, the things that are motivating them and the things that they're calling for, you find some of the things we were talking about. Decision needs, increasing understanding, you've got reference to a hierarchy of models, high resolution models, you've got talk about unified, seamless kind of approach. I also think it's super interesting that you have on your key elements, develop a program for climate model interpreters. We need people to help us, communicate with the people who are going to use the results. But at the same time, you find the description of what they hope will happen as, they call it, evolutionary development, not revolutionary development. So I just think that the community's at an interesting point where I don't think we're at like some tipping point where something's going to implode and something's going to happen, but I just think it's interesting that we have multiple voices at the same time saying, there's something not so good about the way we're doing things, and we could do better. And they have different proposals for what that better should be, and how do we either put those things together or sort among them is the question. It's all in there. And I'm sorry for going into that.
We have about 5 minutes for questions. Gavin, and then Linda, Sharp.
Oh, wait a minute, no, it's always age before beauty.
No, we're swapping. Right. So I think that was very, very interesting. And I think there's one thing that you've missed out.
Okay.
And I think that there's like a kind of overarching kind of theme to what's actually going on that I don't think you actually said. So I think the one thing that you missed out is better access and better databases that allow people to investigate the output from these models in very, I mean, not interpreters, actual databases, easy access data, yeah. So that is actually a very revolutionary concept. CNET 5, however crappily it was put together in terms of how easy it was to get data, was a revolutionary concept, and it will continue to become so. And as soon as we really have active databases on that data, the amount of science that will be unleashed by that is just enormous, and it will be informing both that hierarchy of models and all those different approaches where people can kind of take that information, kind of condense it and make. So I think that's by far the most important thing that is going to be the future that wasn't quite mentioned. The thing that I think that is kind of the bigger picture, which you also mentioned, was that you're right that GCMs and the groups and via the IPCC there has been a greater view on these things because of some of the reasons I mentioned before. Like if you're trying to model what's going on with aerosols, you cannot help but try and deal with the details because the details matter. The same thing for the solar, the same thing for the land surface, the same thing for the oceans. Details matter, and then you have to put these things together. People who are not involved in those projects feel marginalized. And so you have this kind of scientific kind of haves and have-nots in terms of where people are perceiving papers are being published, where people are perceiving, authority is being given, who gets invited to give the keynote things. A lot of that is going to people who work with GCMs, okay? And people who don't feel marginalized. And so there's like this kind of like mumbling of discontent, oh, it's not fair, I'm smarter than they are, and like, we've got this great record, and like, brr. And it's not that that's unfair. I mean, it kind of is unfair, but it's kind of inevitable given that these things are going on. And it's happening in high energy physics as well, right? People who are at the top of the Large Hadron Collider are getting a lot more press and movies made about them than people who are not, right? So, it's just inevitable.
Thanks for your comments. Yeah.
So, let me say this about that. No, actually, on other topics, I have a lot to say about this, but I realize our time is limited. So I think one of the major flaws of perhaps of those three choices that have gotten the most support, if you just look at the list of authors, is one. And there are several problems about that. Number one, and you're undoubtedly aware of this, that statement, and Shuko has made it in a number of different contexts, that it's important because for making these decisions. And it's a very top-down, very much not the, it's very much the predict then act mode.
It's kind of presumptuous.
And, here there have been a very articulate arguments against it by, for example, Mike Kuhn and Suraj Desai. And it seemed like, it also appears to me and I looked at this very carefully because I was very concerned about this, and this is not being recorded, correct? It is being recorded. Okay. I'm not going to say what I was about to say.
Can you edit it out?
Yeah, I could turn the camera on.
Turn it off.
Too bad, you'd really like hearing about this. Another time.
Over.
part of, what Gavin says about who controls these decisions, about that the GCMs are dominant. Absolutely, there's no question. And not only is it dominant, but indeed the players, and becoming a player is not that easy, especially if you don't go along with the dominant paradigm. Here's an example from CMIP 5. Why? And it's so incredibly obvious, and I know they were told about this because, of course, I made the brilliant point myself, that they have this ridiculous Byzantine set of simulations to do, and did anybody think about the number of realizations for each of those? No. And the original plan was, oh, well, do 2 or do 3 maybe. And of course now, 7 years later, we know that that internal variability is incredibly important. Why? Because nobody knew that? No. It's because nobody involved, the small group of people who were involved in that, thought about it. And I think that's a very dangerous situation. So at the same time, I was also an author, by the way, on that advancing climate modeling, and really pushed this idea of the climate interpreters, which we're still trying to get going. I'm not going to try to defend regional climate modeling here. I just really think that, in many ways, like Isaac Held, at least, I think his ideas are very important, and this whole issue of understanding, although I think some of that can be done rather than doing hierarchies, about not always running on to the next new thing, but actually doing a more complete, thorough analysis of the runs we have, and not rejecting runs once we have the newest thing, when we have no way of determining that the new models are really in some way have precious new information to deliver in terms of projections. I rest my case, but I could, as you know, go on and on.
No, it's gone entirely to plan. I said I was hoping to get you guys talking. I don't know. I'm thankful for the comments. I'm just trying to report in a much too brief way on some interesting developments and get people to talk about them. So.
No, it would be good to have this as with a longer discussion.
The fact that they're players and becoming a player is hard. Canadian Science Establishment is now moving more towards an NSF model, and so it's being asked to promote excellence, by which is measured that you have larger grants for fewer people. And I never understood the motivation for that particular thing, but it's a very real impact. So you talked, Judy Curry, you quoted her saying, we're a big, expensive rock. For some people, that's not a bug, it's a feature. I'm just wondering if you have any comments about the politics of granting and these kind of things, what role that's going to play, whether the idealists like me are going to win.
Yeah, I mean, I don't have a lot to comment on it. I think this is something I'm really learning about, because in my experience in the U.S. was that we didn't have that kind of system where there were, fewer grants that were bigger going to, larger grants for fewer people. But I moved to the UK, and that has been my experience, that seems to be more common there, that they have, a small number of big pots of money that people can win, rather than a whole bunch of, a smaller pot that you can divide up a lot of ways. So I'm still, thinking about what this means for research and stuff, and I haven't really connected it with, yet in my mind, with these kinds of things. But toward the end, when I was talking about, who's going to decide what really happens here, I did say that I think that, research funding bodies are one of the, institutions that are poised to have an effect on this, and if they're guided by something like, the National Research Council report, then, there's actually seems to be quite a lot of room for different kinds of activities. But I mean, I'm really just amateurish on this at this point, so I don't have a lot to add beyond that.
I had a couple of good questions. One was, you said, maybe this was a throwaway comment and you didn't quite intend it this way. You did this nice overview of these three different proposals, and then you said there seems to be consensus that something has to change. And I'm not sure that's true, that there are clearly three groups out there saying something's got to change, but I suspect there might also be a silent majority of people that say, you know, actually just carrying on the road we're on is fine?
Yes, no, you're absolutely right. That was just, if that's the way it came across, it was just sloppy
Yeah,
talk
okay.
on my part. I mean, all I meant to be saying was, if you look at, for instance, these kinds of calls, the calls have in common that they want something changed, they disagree on what seems to be the highest priorities for change. But no, I did not mean to be implying that in the community there is agreement that,
Yes.
I mean, yeah.
So then my question, I think, is about the balance between where research is done, in particular the balance between universities and government labs, because the GCMs are all built at large government labs, because universities just cannot do this. They cannot amass the resources, the supercomputing facilities, the critical mass of scientists that you need to build a GCM. So I was wondering if you had any insight into that. So academics that want to engage in climate modelling, what are they pushing for?
I have no idea what they're pushing for. You know, they're not writing feature articles in BAMs that call for
Right.
revolution. So I mean, I have, I only have limited experience of knowing some academic scientists who say are working on, say, a piece of a parameterization that they think would be a valuable addition to certain kinds of modeling projects, and then they have the challenge of getting modeling groups to agree that actually the way they've developed this parameterization is actually a good addition for their model, and that's a challenge, getting yourself in at one of those labs and getting people to have uptake. So, I mean, yeah, it's a great question, and maybe Gavin's better poised to speak to it than I am. I mean, I don't pretend to know anything in general about what the view among academic scientists interested in being involved in climate modeling, large GCM modeling, what their view is.
Well, I think this goes back to my earlier point. The fact that people are now able to access the data and the output without having to be part of the groups has enormously increased the interest in the university community and what these models are doing. I recall back 15 years ago, the university community did what they did, small-scale process stuff, a little bit of that, and then the GCM people did what they did, and there really wasn't that much in the way of interaction. CNIP has changed all of that. Now, has that increased the desire of the university community to be contributing to development? I don't. Is it a really, really hard problem to coordinate developments that are not central to where the most development is? Absolutely. I mean, you can see the tensions at NCAR between the working groups and the DOE in particular that are actually extremely tense right now. I mean, it's non-trivial. I mean, a lot of them, one of the things that really hasn't worked very well with the CMIT process is that the analyses have not come back in time for them to affect subsequent development, right? So people are still working on the CMIT 5 results, and they're doing all sorts of interesting analyses and things, but the CMIT 5 results were done with models that were frozen in 2011, right? So all of the modeling groups have made, enormous amounts of new development since then, and so pretty much anything that they do now is kind of interesting but moot, right? So to really kind of embed the university community in an ongoing development process requires a revolution in how those informations get passed. But I think it's a revolution in communications and structure rather than two rather fanciful and one very sensible points that you came with.
Charlotte, did you have something?
Yeah, I mean, really just wanted to know more what you think about that Manhattan project, in the sense of how much would it help to just increase the precision and the grid when you really don't. When new problem arise, you don't have enough physical understanding. My question was just how much would something like Manhattan project really help without, at the same time, increase physical understanding?
I mean, I I guess it's an empirical question, right? But I mean, I guess the argument is that some of the things that were mentioned in the quote having to do with, say, resolving clouds, and that there are certain kinds of features that we know we're not resolving, right? But that seem really important. And if we did have resolution that was that fine, some of those processes that are thought to be really important could be resolved in a way that they're not. And so you might think that really might make a big difference. But I mean, it's an open question how it would actually play out. There will still be other things that need to be parameterized, and everything will still have to work together. And so I mean, it's not there's no guarantee, but I think there is a reasonable there are reasonable physical grounds for thinking that you might have real benefit from getting down to that scale, but you can't count. Yeah.
There's another way in which that could work. If they build some kind of super model that is really also usable as a weather forecast model, they can do what the ECMWF has done over many years and do lots of iterations of the model, tested, very well tested against observations, and only changed when the model actually improves, so that over time it could, there would be a better grounding in the observation model relationship. Now, whether that would actually work to improve it as a climate model is another question, but you can see that there's some intuitive plausibility to that possibility.
I mean, the Hadley Centre in the UK works on that basic model, right? And they do have, they test everything at the highest resolution with weather, and then down to the resolution of the climate model. But everything is the same code base and things like that. And I think that there is, that there's good utility to be had from that, but it isn't a panacea of producing the best climate model. So, for instance, EC Earth is derived from the ECWMF, ECMWF weather modeling, right? And you know what? It isn't that great at a climate model, because the things that make a good climate model are not the same things that control dynamics on a day-to-day basis. But I think one of the more interesting things about that BAMS article was that it's extreme presumption that just because somebody wants something, that therefore it's possible. People want decadal regional predictions that are accurate. You know what? My guess is that is not possible. And it's not possible because of the basic chaos things that we've been talking about all week. And higher resolution doesn't make it any more possible.
But I don't think that the possibility is about, my friendly reading of the claim of possible is that it's possible to build the high resolution model.
Yeah, and
it's not
necessarily
going to do so. It's not necessarily possible that you get accurate regional predictions over long timescales, but it's possible to say, have a bunch of money put into developing a really high resolution stochastic parameterization,
So the stochastic parameterization thing is a total red herring. So it's not a different thing to anything else that's going on.
Well, my understanding is that that's their answer to concerns about structural uncertainty. To having a limited structure.
It's just another structure. It's like saying,
no,
there are lots of
at
different
this point, I think most of the audience is starting to pay. I still have Wayne and Adrian in the queue. So maybe if they have quick comments and quick responses from Wendy Parker, and then we can call it an evening and discuss this further over drinks.
The answer to my question might be just no. So the question is, can you say more about some of these alternative modeling paradigms that Kirby was suggesting? One of them was network models, another one was stochastic models. How does a stochastic model differ from what we're doing? Because, correct me if I'm wrong, the current models have stochastic elements in many ways, don't they?
Yes.
Yeah. So what does she mean when she says let's do stochastic models, and what's a network model?
Yeah, it's not quite no, but it's close to no. I can't say too much. The stochastic part I think is just sort of having more stochastic elements, so treating more parameterizations in stochastic. It would be an open, maybe even to developing simpler stochastic models that might be, valuable. But the short answer is I don't know. I could if you go to that website of hers that I put in the reference, that's where I've seen the most discussion from her on what she means by those things. So that's my best.
Okay.
But I still don't. I'm still, trying to get a grasp on what it is.
Maybe a quick
question?
So I take it the Manhattan Project move is to say, let's pool our resources and build one model to rule them all. And one of your worries about that was, it'll take too long. And a naive sort of immediate thing you might think about that is, wait. If doing the bit where we all pool our resources is going to take too long, then isn't anything we're going to try and do going to take too long?
I mean, all I was trying to say was that if you're trying to offer this up as if you're giving a justification for doing it, is that, you know, we urgently need a certain kind of information to make certain kinds of climate decisions, that realistically, the time scale on which you're going to be in a position to say you've now got that information is much longer than the time scale on which you need to make those decisions. So it's kind of a not the greatest reason to give. I mean, it's true, it's like maybe it's going to take longer if we wait for, you know, things to go in a different way to have a model like that. But if the basic issue is the urgency of this need for information, I'm just sort of saying, it's questionable whether that's really a good reason to cite for this.
Decision making doesn't really seem to be driven by information.
Exactly. This is something that I meant to put in the slide and didn't, but it's something that Linda mentioned when she referenced Mike Bloom and Suraj Desai, you know, just making the point that it doesn't, you know, the factors that make an important difference are not necessarily these factors anyway when it comes to making the decisions. It's other things. So.
On that happy note, please join me once again in thanking both of our speakers.